Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you today about compound interest and exponential growth. In this presentation, you'll learn how to compute compound interest using exponential functions, and you'll learn how to calculate growth decay using exponential functions as the model for the growth and decay. Compound interest is interest computed on the original investment as well as the interest that is accumulated over time. When we talk about compound interest, it's usually computed over some interval of time that could be yearly, monthly, semi-annually, or quarterly. Lastly, it could be continuously, which is somewhat of a hard concept to think of. This would be where we're computing the interest at each moment in time. We might think of that as computing the interest every second. There are two formulas that we'll use when we're computing compound interest. If the interest is compounded a finite number of times, that is, it's not compounded continuously, then we'll use the following formula here. A equals P, where P is our original investment, multiplied by the quantity 1 plus R over N, raised to the product of N and T. R in this case is the rate as a decimal. N is the number of times interest is compounded per year. And T is the number of years. If the interest is compounded continuously, we'll use this model. The amount in the account is P. P is the original investment, multiplied by E raised to the R times T, where R is the interest rate as a decimal, and T is time. Let's take a look at an example here. We have a young man that wishes to invest $5,000 into a savings account. At the bank, he's presented with the following options. Interest compounded quarterly at an interest rate of 3%. Interest compounded monthly at an interest rate of 3%. Or interest compounded continuously at an interest rate of 3%. The young man's planning to invest his money for 20 years. And so he's wanting to know which option will give him the most money in his account after the 20 years. Taking a look at our different models, the first two options, the interest is compounded a finite number of times per year. And so we'll use the first compound interest formula to compute those. And in the third option, where his interest is compounded continuously, we will use the second model. Taking a look, our initial investment for each of the three cases is the $5,000. Here our interest rate is 3%. And notice in each of these instances where the interest rate is put in, it is put in as a decimal, right? It's not put in as 3, it's put in as 3/100ths. In option A, here N is 4. And N is 4 because this is interest that's compounded quarterly. so it's compounded 4 times a year. And in option B, we have N as 12 because it's compounded monthly. And so 12 times a year. And again, in the continuously compounded interest, we don't have to worry about a value of N. All right, we put these into our calculator and round to the nearest cent, and we get the following totals here. And we can see that the numbers here, as we look from option A, B to C, the values are larger each time, and that corresponds to an increasing number of compounds from 4 compounds per year to an infinite number of compounds per year continuously. So continuously compound interest will give you a higher amount of money in your account. You'll notice it's not it's not an incredible difference. Talk about exponential growth and decay. Exponential functions are great to model this kind of growth or decay because exponential functions either increase rapidly or decrease rapidly depending on the equations. Exponential growth and decay model is actually nothing different from our continuously compounded interest formula. So the same formula that we use to calculate those continuously compounded interest problems, we can use to model growth and decay. The only difference here is that our growth rate could be negative, could be less than 0, and in that case we would be modeling exponential decay. Let's take a look at an example. Researchers are studying a new strain of a certain bacteria by observing the growth of the bacteria in a petri dish. They begin with 100 bacteria in the petri dish and measure the amount of bacteria each day. The researchers model the growth of the bacteria with the function A equals 100 e to the 0.3 t, where A is the amount of bacteria t days after the bacteria is placed in the petri dish. We're interested in knowing how many bacteria will be in the petri dish after 7 days and how many bacteria will be in the petri dish after 100 days. Using the exponential model, we can plug in our values of 7 days and 100 days. Input this into our calculator. We get the following for part A. We would have 817 bacteria. And in part B, we put this into our calculator. We get what is called a quadrillion, 1 quadrillion bacteria. That's all answers here rounded to the nearest whole number. Taking a look at these two results, you can see the nature of exponential growth. Started with 100, and then after 7 days, we were already at 817. And then from day 7 to day 100, what an increase there, all the way to a quadrillion.